Hello, everyone. Welcome back to Grade 12 University Physics. Here with Mr. Stone. So here we're in Unit 1, Lesson 4, and we're gonna change gears a little bit, and we're gonna talk about gravity. Okay, and we're gonna go sort of a different format today. We're gonna go less math and more story. Okay, so the development of gravity as a theory, as an understanding of celestial mechanics, is a is a great sort of case study in how science is done. Okay, the process of science, of how we go from data to theory, uh, figuring out how things work, and it doesn't matter what it is, but the way that gravity sort of developed, the way that we got to a universal gravity formula, the way that we got to the idea that all masses, any mass that exists, um, generates a gravitational field that, in our modern day view, sort of changes the space-time curvature. Uh, this whole development is a fascinating way of looking at how science works. So we're going to start our story in Denmark. Okay, with an interesting character. There's a guy called Tycho Brahe. Um, he's a Danish astronomer, and this is in the 17th century. So quite a long time ago, and this guy was a bit different. Okay, so one the thing that we care about is that he developed a way of analytically following the movement of planets and stars and anything in space. He developed a way to organize his data to come up with incredibly accurate and incredibly painstakingly put together measurements of celestial measurements. And he got this thing which he called the Star Catalog D, that basically had all of his measurements, and it was just a huge collection of data. Okay, so he didn't care about any of the whys at this point. There was no whys at this point. The we're talking about 16th, 17th century Europe, where the idea was that angels push the planets around in circles. And we were just coming to terms with the idea that we are in a heliocentric uh, solar system, that the sun is in the center and not the Earth, right? So this is still quite a long time ago. So what he did, all he did was come up with a lot of numbers, a lot of data. Okay, and just quickly before we move on there, um, from a historical point of view, he was pretty insane. He lost his nose in a duel, and he replaced it with a gold prosthetic. Um, he actually saw the first supernova in 1572, and he called it a nova. This was a new star, and he actually discovered one, which we call now SN 1572. That's how supernovas are designated. That number at the end designates the year in which it was discovered. Like, for example, SN 1987 is one of the more recent ones that's quite famous. He had a pet elk. Um, Unfortunately, the pet elk fell down the stairs. Um, he had a dwarf, and he was incredibly wealthy. Uh, from just one of these very eccentric gentlemen's scholars of the 16th, 17th century. Okay, and that was Denmark. Okay, so now we've got to the point now where we have a big data set. Okay, so this is what we call empirical physics or empirical science. We don't worry about the why, we just collect all the data. And then along came another guy. So one of his assistants was a man named Johannes Kepler, who ended up actually working as the imperial mathematician of the Austro-Hungarian Emperor Rudolf II in Prague. He went and he collected all that data, and he went over it to try to figure out if they're related in some way. Okay, so this is not wondering about why. He was just looking for relationships, just like you guys did in that that analysis of an experiment assignment is you took a data set and you manipulated it until you could actually come up with a relationship. I think it was t equals 20 root d over r squared, something like that. So you just took the data and playing around with it, you were able to come up with a relationship. So he did this as well, and he played with all the data and developed what we call Kepler's laws. These are Kepler's laws of celestial motion, of how planets and things go around. And the important one for us, the one that we're going to move on from, is his third law. His first law was about the shape of orbits. Orbits not being circular, they're actually elliptical, like ovals. And his second law states that the area swept out, well, basically the speed that they travel, depends on how close they are to the planet. Okay, so this all came from a purely empirical viewpoint. Again, empirical meaning data. So you take the data and you try to figure out relationships. You don't try to answer the question of why this is happening. You're just trying to understand how it's happening. And his third law, the one that's important here, is that the period of a planet's orbit, so the time it takes for the planet to go around the sun, is proportional to the 3/2 power of its radius. Okay, so as we increase the radius by a certain amount, we increase the period by a 3/2 power. It just seems like a strange thing, because well, you could also say that the period squared is proportional to r cubed. That's another way we can. Those are equivalent. Maybe that makes more sense to you. But just know that as we increase the period, as we increase the radius, we got farther and farther away, we increase the time it takes. And we're not just increase in any way, there's actually an analytical way that you can come up with that. All right? So now we have an important development after this. We get to Newton, Sir Isaac Newton. So he was able to take Kepler's data and Kepler's empirical understanding and develop a bunch of theoretical ideas, underlying theoretical ideas that go beyond just celestial mechanics in his 3 laws. All right, so he came up with Newton's 3 laws, which you should be familiar with. And he was able to then go from Kepler's laws, taking into account his 3 laws, and actually developed a universal law of gravitation, a theoretical understanding of gravity anywhere. Okay, so Newton, just quickly here, arguably the most important mathematician of the last 1,000 years, possibly. There's other people up in the running there, like Gauss or Euler or even Leibniz. But just in terms of influence, probably Newton could be argued. But these are subjective. He wrote something called Principia Mathematica, which outlined his 3 laws and basically wrote the book for physics for the next 3 centuries. Nothing really changed fundamentally until Einstein came along. He invented calculus. Don't tell Leibniz, because Leibniz did it at the same time, and there's a big fight about who did it first. And so his Principia Mathematica, that was his first volume. He actually then went on to write a bunch of more volumes. He lived to be like 75 or something like that, even though he would ingest mercury on a regular basis. And from that point, so he wrote that Principia Mathematica when he was 25. The next 50 years was mostly spent doing things like alchemy, trying to turn lead into gold and other weird occult studies. So really, say maybe he peaked when he was in 25 or something like that. He did some. He was the mint. He was in London. He ran the mint. Basically, came up with a standardized currency for the first time. Very, very important historical figure. But the important part that we care about is that he took Kepler's laws and, using his three laws, was able to come up with universal gravity. I'm not going to go into how he did that. I'm going to put a link in the video here. You guys, if you want, it's a pretty in-depth. It's just pretty straightforward, but it's quite in-depth derivation. So, and this professor at I think Leeds, um, I forget, Thomas Garb, I think his name is, has a video on YouTube that is it's actually a 3-part video. It's like 3 hours long, but I put a link in the video description, time-stamped to the derivation if you want to check that out. Okay, but the important part is we got to Newton's law of gravity, which states that the force is proportional to the mass and inversely proportional to the inverse square of the radius. Hopefully that's familiar. The F equals m1 m2 sorry g m1 m2 m1 m2 over r squared. If not, there's a lesson from my grade 11 course that I'll also put in the video description that you can watch as well. But before we come up with our formula, we have one more interesting historical figure, and that's Henry Cavendish. So Newton was able to come up with the relationships, that the force of gravity is proportional to something's mass and inversely proportional to the square of the distance away from it. He wasn't able to come up with the constant that made it equal for a little while, until this guy, Henry Cavendish, came along and did a whole bunch of very careful measurements. He's a very secretive guy, okay? So very shy. He was another one of these gentleman scholars. And we didn't even know how much stuff he did. Some of his notebooks have been found 200 years later. And going through them, there's a whole bunch of things that he may have discovered before they were actually discovered publicly, because he just never published any of his data, any of his results. Very strange guy. But his most famous work is that he was able to show that the proportionality constant for Newton's universal gravity is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And again, hopefully you've seen this before in grade 11 physics. And again, if not, go check out the video. So we put it all together. Oh, sorry. This is his apparatus to. So we have these two larger masses here and two smaller masses here. And this, the smaller masses are able to spin. I think that's how it was set up. Forget exactly. One of them is able to spin. He was able to move things around, and there's a little tiny mirror here, and he was able to see tiny deviations in the rotation. And he was able to very, very carefully see how much these masses would affect each other. And he came up with the constant. And we put it all together into Newton's law of gravity. All right, that the force of gravity is G, this constant, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, multiplied by the two masses that are interacting, divided by the distance between them, r squared. Now, you may be a bit confused with the idea that that's r as a radius. Now, remember, what we're actually looking at is, if let's say we have two masses, m smaller m, capital M. If we have our frame of reference defined by, let's say, smaller m, there will be a sphere of influence of the mass m here of a radius r. That's why we're using radius. This force is spherically symmetric. Doesn't matter where you are on that sphere, you'll have that same influence. That's what I mean by spherically symmetric. So this other mass, capital M here, will feel a force towards it, and applying Newton's third law, that action force will then also have a reaction force, so there'll be an attraction of the two. Okay, so r is the distance between them, but really is a radius around one of them. I could change this viewpoint as well. I could change my frame of reference to capital M, and it would be the same thing. it would be r distance away from lowercase m. But just a little bit of confusion then with the r. Okay, whoops, let's get rid of all that. All right, now let's do an example. So force of gravity, GMM over. What is the magnitude of the force of gravity between two students socially distanced at 2 meters if they both weigh 65 kilograms? Okay, so two students, they're 2 meters apart. How much attraction is there between them gravitationally? Can't be too much, but let's find out. So we're going to plug in our numbers into our formula, 6.67, 10 to the negative 11 Newton meter squared per kilogram squared, times 65 times 65, or 65 squared, divided by 2 meters squared. Careful your units. This is in meters, so the meters would cancel. Kilogram squared cancels with kilogram squared. We'll be just left with newtons. And the answer is 7.8 times 10 to the negative 8 newtons. Or what would that be? 0.7 nanonewtons? Oops. What's happening? What did I do? Uh-oh. So let's go back here. So that's going to be 0.7 nanonewtons. Okay? And a therefore statement. Finish our problem. So not very much. But there is a force there. The reason why we think of gravity is incredibly weak, right? 65 kilogram masses are only feeling nanonewtons when they're 2 meters apart. The reason why we consider gravity, like we feel gravity is like a strong force, even though it's incredibly weak. It's about 10 to the negative 40 times weaker than electricity. The reason why we think of it as being strong is because our experience with gravity is the Earth. Right? We're sitting on a 10 to the 24 kilogram mass. We're sitting on this rock that weighs a million kilograms. Because of that massive mass, we experience a strong force of gravity. But really, on a universal scale, gravity is quite weak. So these questions that goes with this lesson, not too difficult. It's basically just manipulating that formula. 12 is a little bit more complicated because it's a vector problem. So we're asked to find what is the magnitude of the net force on M1 here. So that's going to feel a force, right? It's going to be attracted towards M2 if we define, let's say, X, Y. So it's going to have a force of attraction in the X direction, right? F2 this way. It's going to have a force in the Y direction. Let's call this positive Y direction, right? F2 is going to be, just F4, sorry. That's going to be down in the Y direction. And then there's going to be one at 45 degrees, which we're going to have to break up into components. So we're going to have to break this up into an F3 in the X and an F3 in the Y. And then we can add all the components up together, and then we can get our final answer. Okay, so break it up into components, add all the components, make the components into a final thing, find our total using Pythagoras to find our hypotenuse, which is going to be our total F, and then using trig to find our angle. Okay, hopefully you did problems like these, component problems like this in grade 11. If not, check my answers and see how I did it. Okay, and 13 is a fun little problem of finding out how heavy the Earth is. Using gravity, we can find out how heavy the Earth is. All right, so that's all I want to talk about in terms of like a grade 12 level of what is gravity. But I just want to, since I'm here, why don't we spend a little bit of time here? You can stop now, get your lesson done if you want. But we can talk a little bit about our modern view of gravity, because we got to about, this was in the 17th century here, where Newton was doing his work. And a lot of stuff has happened since then. And really, nothing really changed until the early 20th century, when relativity showed up. And things got really strange. And what gravity is changed fundamentally. Our modern view of gravity is a little bit different, and it basically it says that a mass will bend the fabric of space-time. It'll cause a dip, and you can think about it like when you stand on a trampoline. You stand on a trampoline and you toss a bunch of marbles. The marbles will be attracted towards you, right? The marbles will go down the curved surface of the trampoline. But the problem with that analogy is that's a two-dimensional view, just like in this little animation here. Gravity is actually three-dimensional, well, four-dimensional. So we're manipulating a four-dimensional trampoline. Okay, we're changing the curvature of a four-dimensional trampoline, and that hurts everyone's brain. Nobody can think in 4 dimensions. Let's look at a two-dimensional picture here. So we're bending in the third dimension. We're taking this two-dimensional plane and bending it in the third dimension. Really, we're looking at a change in the fourth dimension, which would then end up changing our curvature. So here's a nice little picture of what we mean by this. Is our sort of our frame of reference becomes manipulated in another axis, and it changes. So objects appear to be traveling along straight lines on a curved frame of reference. Okay, so even though objects appear to be traveling in a straight line, they aren't. It's because of where they're like the marbles think they're traveling in a straight line, but they're traveling on a curved line in 3 dimensions. So that's how we picture gravity. And it gets even more complicated because gravity even can travel in waves. Gravity travels at the speed of light on a gravity wave. And we know this is true is because we've actually been able to measure them. We've actually been able to see them. This is a incredibly violent event in space that you're looking at. This is a collision of two black holes as they start spinning around each other faster and faster in the incredibly short time frames we're talking about here. We have these two black holes actually collide and produce massive gravity waves. And these gravity waves are able to, get to Earth eventually. And what they do is they actually change the meter stick in which we measure our space-time, where our local space-time, and we can actually see that. If you're wondering why I'm sitting here in a bunker, I'm actually sitting at the detector that detects these waves. This is LIGO. This is the laser beam. This is the main laser that they use as an interferometer to see the gravity waves, because the gravity waves actually, this is a 4 kilometer long laser, and there's two of them at right angles, and as a gravity wave comes along, it actually takes the actual space itself and compresses it or expands it, and that changes the path length of that laser, and it actually interferes with another laser, and we're able to get these tiny ripples in space-time. Even though this is an incredibly massive event that releases more energy than our sun will ever release in its lifetime, the gravity waves, because gravity is so weak, is incredibly weak, and we have to use this incredibly powerful, double right angle 4 kilometer laser interferometer to see this. But we can, and this is an animation of what happens, the ripples that are happening when two black holes, which itself we don't even understand, let's not worry about that, incredibly massive pinpoints in space, collide and merge into a bigger black hole. And that's the wave, the ripples that we eventually get, which we eventually see. Yeah, and mathematically, this is horrific stuff. We're never going to worry about the math. This is Einstein's equation. That yeah, it's pretty gross, but really, it's not that bad. It looks disgusting, but basically it says there's physics on this side. Okay, this is the stress tensor that basically defines how things behave, and this side is just geometry. This is just how we measure space-time. This is measuring the curvature of space-time. So really, it just basically says that the curvature of space-time defines the physics of things. Um, how we actually have space-time bent and manipulated and whatever actually tells us how things behave. Which probably by the end of this, your head hurts and there's a lot mind blown. Okay, so hopefully that didn't confuse you guys too much, but just a quick little overview of our modern view of gravity. It gets really awesome, pretty confusing, but pretty awesome. Okay, so just work on those problems, and we'll be talking to you later. Take care, guys.